It's my privilege to introduce our distinguished speaker tonight, Dr. Dale Klein. He is an Associate Vice Chancellor for Research of the UT System and also a UT Mechanical Engineering Professor. The title of his presentation is U.S. and World Nuclear Energy. And I really encourage you to not be shy. Dale is, if not one of the most expert, the expert. And so he's on the Fukushima post-mortem, or what's the commission there? The committee? Nuclear Reform Committee. So he has in-depth, he may even have charts on this, I hope, in-depth knowledge of this. He's been there in the bunny suits. He's there trying to help the Japanese TEPCO and the government understand what to do differently. So please don't be shy with that. Chernobyl also. Anything that you have a question for, please don't be shy. So let me go through the rest of his distinguished resume here in the short bio. He's been associated with the University of Texas since 1977 in a variety of administrative and academic positions, as well as a professor of mechanical engineering in the nuclear program. He served as a presidential appointee to the Nuclear, Chemical, and Biological Defense Programs at the Pentagon. He was a commissioner at the U.S. Nuclear Regulatory Commission from 2006 to 2010, and also served as a chairman during 3 years of that. And then he returned to UT in 2010, I guess before traffic really got bad, as a professor of mechanical engineering in the nuclear program and as an associate director of the Energy Institute. In 2011, he became the associate vice chancellor for research at UT and the UT system. He serves on the board of the Southern Company in Pinnacle West, Arizona Public Service, and he currently serves as the chairman, not just a participant, but the chairman of the Nuclear Reform Monitoring Committee for the Tokyo Electric Power Company, TEPCO. That's the company that owned and ran Fukushima, and has expert knowledge of the Fukushima disaster. In addition, he serves on the Committee for Nuclear Power, advising the UAE of their nuclear program. So please join me in welcoming Dr. Dale Klein.
That magic button? Okay. You probably can hear me anyway. I'm used to yelling. And one of the things that, having been a faculty member for a number of years, I tend to pace around. I learned that moving targets are harder to hit, so it's important to do that. What I want to do is just basically give a little background on nuclear and then talk about where it fits in the world picture as well as in the U.S. And then at the end, I've got some slides on Fukushima. And that is, if you ever need a serious reminder of nuclear safety, just go to a place like Fukushima. It is very sobering when you see that activity and why nuclear safety is so important. So it's always good to let you know what I should be talking about. But I wanted to basically give a little bit of a background on nuclear in general, some just basic information. Talk about the world energy, because right now nuclear energy is very important in the world, not as important in the U.S. When I left the Nuclear Regulatory Commission, we had 19 applications for 28 reactors. Only 4 of those are being built. Why do you think that is? Natural gas. So when I was chairman of the Nuclear Regulatory Commission, I asked the president of Exelon what it would take for him to build a merchant nuclear plant. And he wanted $8 a 1,000 cubic feet for natural gas and a $25 ton carbon tax. We are a long way from that. And so just on economics, in the U.S., nuclear is not favorable now. Now, if you look at other countries where you have to import a lot, and if you look at another country like even Japan, where energy security is a big deal, because if those ships stop bringing in oil, LNG, and the oil, then that country is vulnerable. At the other side, you look at a country like the United Arab Emirates. They're building 4 nuclear plants all at the same time. Monster site. They have about 20,000 workers on this site. I go there about every other month, about 8 times a year, and the amount of construction there is phenomenal. So you sort of say to yourself, why would a country like the UAE that has tons of oil and gas build a nuclear plant? And again, it gets back to energy security. They don't want all of their electricity from one source, so they want diversity. They also want to look long-term, and they realize that while natural gas and oil is low now, it's not going to stay low for 60 years. And so they're looking at basically the return on their investment. And in a few years, they can sell their oil and gas for a lot higher price than it will cost to generate it. So different countries will make different decisions. So we'll talk a little bit about that. And then I'll talk about Fukushima, but as Dave indicated, the real fun part of these is your questions, because that's what I'm here to do, answer. And if they're hard, I'll let Del Tesser answer them. So we'll look at that. So let me just, in case you want to go out and build your reactor, after this talk, I'll tell you sort of the key elements that you'll want to do. The way nuclear power plants work is they generate heat. And the way they generate the heat is you go out and you find a friendly atom, and the one that's used in our commercial reactors is uranium-235. And if a neutron hits uranium-235, it becomes unstable. It'll split into two fission fragments. And so when you talk about nuclear waste and concerns, some of these fission fragments are radioactive. So when you have a fresh fuel pellet, you can hold it in your hand. It's not a problem. But after it's been in your reactor for about 3 to 4 years, you would not want to hold it in your hand, because some of these fission fragments are radioactive and they have to be handled very carefully. So basically the chain reaction, you start with uranium-235, hit it with a neutron, it splits, that neutron goes off to others, and so the chain reaction is self-sustaining. So the way this works is you'll take a little fuel pellet, it's about half an inch in height, about half an inch in diameter, ceramic uranium dioxide fuel, enriched to about 3 to 4% uranium-235. And the amount of energy in that little pellet is fairly phenomenal. It's equivalent to a ton of coal, or 17,000 cubic feet of gas, or 149 gallons of oil. So it's a very compact form of energy, very efficient. Because what you're doing is you're dealing with the nuclear forces rather than if you burn something. If you burn something, whether it's coal, oil, or gas, you're dealing with the electron clouds, and those are weaker. So if you look at forming a CO2 molecule, you'll get roughly 2 electron volts when you form CO2. If you split your friendly atom of uranium, you get 200 mega electron volts. So that means you get 100 million times the amount of energy from that fission reaction than from burning something, because you're dealing with the stronger nuclear forces. So that's why it's such a compact form. Now there's people like Dave and I that think reactors are fun, but you really do it because they're energy efficient, and in general, until we had very cheap natural gas, they were economically advantageous. So I gave a talk a number of years ago in Dallas. It's also equivalent, that pellet, to about 50 gallons of gasoline. And so the student held up his hand and said, well, if I put that little pellet in my car, can I drive it around? It doesn't work that way. You've got to go through a conversion process. So these little pellets just simply stack up in a long rod, and this rod then goes into what's called the fuel bundle. So during the fissioning process, this pellet gets hot because of the slowing down of the fission fragments and converting mass into energy. This rod gets hot, and so all you do is you flow water by it, and the water gets hot. So all a nuclear reactor does is makes hot water. It makes a lot of hot water. And so we typically have 2 different kinds of reactors in the world. We have the main one is called the pressurized water reactor. And this really spun out of the Navy nuclear program. That's why it sort of started a little bit faster than the boiling water reactor. So in the United States, 2/3 of our reactors are pressurized water reactors. And this reactor has 3 distinct loops affiliated with it. So in this area, the primary loop stays liquid all the time. And so the water goes by the rods, it gets hot, it comes out, it goes through a steam generator, and in this second loop is where you turn water into steam, and then that steam then goes through a turbine. So you'll have 3 different loops. So the water that stays here all the time. It just goes around and around. Then you'll have the secondary steam loop, and that water is closed, goes around and around. And then your third loop is the cooling water. So you'll either have a cooling tower, a lake, a river, or something like that condenses that steam back into liquid and it circulates around. So it's a very basic type of reactor, and that really came out of the nuclear Navy program and was commercialized. The other kind of reactor is a boiling water reactor, and this is the kind that was at Fukushima. And it doesn't mean that boiling water reactors are inherently unsafe. It just means that this particular reactor at Fukushima was a boiling water reactor. In this one, you only have 2 loops. The vessel is taller, and so you'll actually make steam at the top. You'll have steam separators, so the water droplets are filtered out, and that steam then goes through the turbine. Again, it's condensed down and comes back in. So that one will be a 2-loop plant versus a 3-loop plant, but you'll actually convert the steam inside of it. The vessel is about twice as high as in a pressurized water reactor, but they're essentially the same concept. Some people would say which one was better. I used to say, well, it's like a Ford or a Chevrolet. Would you rather have a Ford or a Chevrolet? So, they're similar. Now you have to say a Mercedes or a BMW because the costs have gone up so high. So we have to use a different analogy now. So if you look at around the world and you say, well, why would anyone want to build a nuclear plant? And usually there's a variety of reasons. One is diversity. You don't want to have all your electricity from a single source, no matter what that source is, whether it's gas, whether it's coal, whether it's oil, whether it's nuclear, whether it's hydro. You want energy diversity. The other thing is they build nuclear plants because they are sustainable. There are tons and tons of uranium around. So if we took all the uranium that we know today, you could run all the nuclear plants for their entire lifetime with no problem. And that's at a very low uranium cost. If the uranium cost goes up, then your supply goes up. So it's very sustainable. In addition, you could also build a breeder reactor where you actually make fuel as you create fuel. Or as you burn the fuel, you make it. So if you look at the fission from a uranium-235, you get, on average, 2.5 neutrons. That doesn't mean that you have a half a neutron. Sometimes you have 2, sometimes you have 3. You only need one of those to keep that chain of reaction going. So you could take that other, on average, 1.5 neutrons, and you can convert a fertile fuel to a fissile fuel. And that could be either thorium or uranium-238 to make plutonium. So there's enough depleted uranium in Paducah, Kentucky, and in Ohio for the weapons program that would sustain all the United States electricity for 700 years if you put them in a breeder reactor. So it is a very sustainable kind of energy. And then the final reason is economic consideration. If you look, for example, at a country like Japan that has to import 98% of its fossil fuels, their financial situation is different than what you see in the United States. So economics plays a big role. And in fact, that's why they were built initially. If you look at in the world, the electricity demand is still going up. It's slowed in the U.S., but if you look in the world, and if India, as an example, is ever going to come out of poverty, they're going to have massive amounts of electricity for their population. If you look around the world, those countries that have more electricity have better standard of living, better conditions, and so if you want to lift people out of poverty, you can do it through electricity. So if you look around the world and you want to know how many reactors are around, we have roughly about 435 in the world. And if you look at and you talk to a lot of people, they tend to think that France is kind of the world leader, but that's because they get about 75% of their electricity from nuclear. If you look at the number of plants in the world, the United States is by far the largest. So if you look at France, they get 75% of their electricity from nuclear. Why do you think that is? There's 4 reasons. Any guesses? That's a good. So the reasons are no oil, no coal, no gas, No choice. So they made a policy decision a number of years ago that they would not be dependent on other people. And so their energy security to them was very important, and that's why they went that particular route. So you can look, and if you, I'll show you another slide in a little bit about other reactors. But if you look on here, you don't see China as a major player, do you? Now, so the next slide is who are building reactors around the world. And there you will see a huge change. In addition, China is still bringing on about one coal-fired plant a week. You know, their demand for electricity is huge. And so while they're building 28, they're also building a lot of other plants, heavily fossil fuel driven. So in the United States, we have 4+1. We just started a plant up, TVA, Tennessee Valley Authority, had a plant that was stopped in the 90s. And so they just finished it, Watts Bar Unit 2, so it just kicked in. But there are 4 plants under construction in the United States right now, 2 in the state of Georgia by a Southern company, and 2 in South Carolina by SCANA. Now the challenge of that just happened in a few weeks. Any of you heard about a company called Westinghouse that may declare bankruptcy? Bankruptcy is not a happy situation if you're trying to build a nuclear plant, so it's not clear how that's going to shake out, but it's clearly not going to be positive for those 4 plants if you're a vendor.
Is that also true in Korea, their involvement there?
In Korea, what Korea did, the question was it the same as in Korea? And Korea basically had an agreement with Combustion Engineering that is now owned by Westinghouse. In other words, they ended up, but the Korean plants are basically Combustion Engineering. They're a 2-loop rather than a 4-loop plant. And so there are some intellectual property that ties back to Westinghouse, but it's not clear what that will impact. So the 4 reactors that are being built in the United Arab Emirates are being built by the Koreans, designed by the Koreans, built by the Koreans, and will be partially operated by the Koreans. But that one will not be as impacted by the bankruptcy as the 4 plants under construction.
About the 81,000 that the Chinese are building?
That's going to be interesting. I don't know the financial. The question was, what about the 4 AP1000s that China is building? So China has an agreement with Westinghouse to build 4 with an option for another 4. So they're going to be building 8 in reality. Now, the thing that was interesting, when that contract was done, everyone knew that the intellectual property rights would be borrowed by the Chinese over time. So the Chinese now are plan to do a CP 1400. So they want to kick the megawatts up from roughly 1,000 to 1,400 megawatts. It's actually a little higher than that. But what's interesting is Westinghouse first designed the AP 600, which is passively safe, which means if your pumps shut off and you lose all kinds of power, it's not going to melt. The margin of economics was borderline, so they kicked it up to 1,000. They reduced their safety margin, but they still had significant, that it's still passively safe. The CP 1400 is no way that can be passively safe. They will have to have active systems. So they will make a CP 1400, but it will not be passively safe. It's not clear what kind of impact that will have on China, other than the fact that somebody will end up buying Westinghouse. It's just a matter of who and how, and so it's the intellectual property, the systems engineering, the basic designs, and the property rights. So that we will have to see how that plays out. So the rumor is by the end of the month, Westinghouse may or may not declare bankruptcy. It's all unknown at the current time. As David indicated, I'm on the board of the Southern Company. And so they're the ones that are building the two in the state of Georgia by Georgia Power. So I've been on a phone call about once a week on what we think is happening with the bankruptcy situation, because it will be an impact and it's not likely to be positive no matter what happens. So if you go down the list, you can see Japan actually had 2 reactors that were under construction. They're really stopped, but they may kick up again as they look at their demand. But the big one that's out there that is building the most plants right now is in China. So the thing that if you're going to go out and build a reactor today in the U.S., what's different today than it was in the 70s when we were the ones that were building 28 reactors? And a couple of things that happened was that in the old days, you had a 2-step process. You had to do a construction permit. Then after you built it, you would have to come back to the Nuclear Regulatory Commission for a mother may I. And so after you spent $5 billion on a reactor, you'd have to come back to the regulator and say, please may I now operate it. A lot of companies were a little nervous about that after you spend a few $1 billion. And so I used to give an example for my students on a quiz, is just calculate the daily interest of $5 billion and pick a nice number like 5% interest. And those are real costs. So when a plant is delayed and you're sitting on $5 billion, it's not a trivial situation. So a lot of the reactors that were delayed caused the price of those plants to skyrocket just because of the interest rates. So what happened in the early 90s, the regulator and the industry got together and said, is there a way we can do it without compromising safety? And they came up with a process called a combined operating license. So you basically come up with a certified design that the Nuclear Regulatory Commission approves, and then if you build it like it is designed with inspections, then you can operate it without coming back and get thrown into courts. And so that is a big change. It turns out the first application for a combined operating license occurred in Texas. The South Texas project was going to add 2 reactors at their site. And so they were the first application that received, while I was chairman, so they gave me a leather-bound, actually it was on a CD, but they gave it in a little leather-bound book just so I could have one for a souvenir. The other thing that happened, most of the plants that were being discussed when I was at the Nuclear Regulatory Commission were at brownfield sites. So they were existing sites. So if you look at the South Texas site, it was designed for 4 reactors, but they only built 2. Comanche Peak near Dallas-Fort Worth was designed for 4. They only built 2. So almost all the applications we had were at brownfield sites. The other thing the Nuclear Regulatory Commission did was they would let a utility bank a site. So what you can do is you can come in and you can do an early site permit. You don't have to even specify the kind of reactor, but you define the parameters, and you could build either a boiling water reactor or a pressurized water reactor that NRC had certified, and you could get an early site permit that was good for 20 years. So you can bank that site if you want to come back and build later. So several utilities have done that and are doing it. But the big difference in this is having a certified design, a standardized plant, and that's where France did a lot better than the United States. They had one utility that was government-owned. They had one vendor that designed the reactors, government-owned. So they could force a standardization. So what they would do is they would freeze the design for 5 to 10 years, and then they would come out with a new model. So they would make all the improvements in batches rather than in the United States. We at one time had 104 plants running, and we had 104 different ones. Even at a site like Palo Verde that has 3 reactors at one site, they're all slightly different. So now let's move to the interesting area of Fukushima. Yes?
Sorry, may I ask a question about licensing?
Yes.
I was wondering if you could speak at all about the Nuclear Energy Innovation and Modernization Act, I believe it is, that further restructures the NRC's licensing process with the assumption of making it like more efficient for advanced reactor designs? How do you anticipate that?
Yeah, that's a great question. So there's one thing I learned while I was chairman of the NRC. I had 535 advisors. I had 435 in the House and 100 in the Senate. So you learn you have a lot of input, whether you want it or not. And the thing the good news, the Nuclear Regulatory Commission is an independent agency. So I was at the Pentagon for 5 years before I went to the NRC, and there I was in the executive branch. So I would oftentimes be in White House meetings representing the Secretary of Energy or Secretary of Defense. But at the NRC, I was never at those meetings because I was not part of the executive branch. So it's an independent agency, but with congressional oversight. And so that's the difference. So this Congress Act that's coming through is really directed more to new reactors. And the Nuclear Regulatory Commission is very well equipped to handle and analyze light water reactors. So that's what all of the pressurized water reactors, light water reactors. But if someone comes in with a liquid metal reactor, then they haven't looked at it, and they may or may not have the technical expertise to really do it. So this is an attempt to let them get technical expertise to look at these advanced reactors. So it's a positive step. The other thing that I learned as a recovering regulator is the staff of the NRC are conservative. And so if you look either in your jobs now or jobs you will have, you typically don't want to make a mistake, so you will add margins. Well, if you have a 4,000 size agency and everybody adds a margin, at the end of the day it gets kind of big. And so it can become unnecessary bureaucratic and unnecessary delays, in part just because people are uncertain about a decision. They'll want to be conservative. And so my job was to ensure that our staff had the resources and the ability, and that they would make a decision, and that they could justify it in a timely manner. And so, for example, we had a process. The first design certified reactor, we had enabled that to be done in a 48-month period, but about 24 months of that was for litigation. Had nothing to do with engineering, had nothing to do with science. It was litigation. And so once you get through that once, then the next one should be a lot quicker. So I wanted to get our process down to, and the staff agreed for 24 months, but I wanted them to get down to 18, so that when someone comes in with an application, there's no reason it should take 24 months. No reason it should take 48 months. What this will let the NRC do is hopefully make a better decision in a more timely fashion with no compromise on safety, and let the NRC build the technical capabilities that they currently don't have. The NRC's budget, 90% of the NRC's budget has to be recovered from those they regulate. That's a congressional act. So they only get 10% of their budget through the congressional appropriations, but we still had to go through the same bureaucratic process that every other department had to go through, get the OMB certification, and it's not a pretty picture to go through that activities. But they really need to give the NRC additional funding to make those decisions in a timely manner. So it should be positive.
Bill, you have so much experience. I would appreciate that you would respond to this particular question. Availability of the nuclear reactor is fundamental. And in the 70s, it was about 70%. What is the more recent history of availability of the nuclear reactor?
One of the things that happened in the U.S. is it was even worse than 70%. So in the past, the average capacity factor of a nuclear plant was about 60%. And so that meant that only 60% of 365 days it would be running. Now it's 92%, with no compromise on safety. And that's about as high as you're going to get, because you have to shut down for refueling and maintenance periodically. So So it's the highest in the world, and it's done, again, with no compromise on safety, but just better planning, better procedures, better communication, better training, all of those sorts of things. So the capacity factor, if you look at it, if you go from 60% to 90%, you have added thousands of megawatts of electrical generating capacity just by running your plant more efficiency. So that has made a big difference. So now we're going to switch and talk about when things go wrong and how they go wrong. So if you look at Fukushima, it's located on the east coast, and Tokyo is down at that little spot. What's interesting about Fukushima is that on this site where the reactor was picked, there was a marker that was put down in the year 869 that said, don't build here. So all along the east coast of Japan, there are these old stone markers that history had said for a variety of reasons you don't do things. Not only did they build it there, but they dropped it down 15 feet so they wouldn't have to pump water up and they wouldn't have to ship and raise all the equipment up. So if you want to look at a root cause of that accident, was you never should have built it there. Or if you built it there, you had a lot more safety systems. And so when you look at the fundamental reason of Fukushima was a bad location. If that reactor would have been higher elevation, not a problem. And so I'll walk through that and show you what happened. So by the way, so what happened, the reactor was designed for an 8.2 earthquake, and what it experienced was a 9. What's interesting is that all their safety systems worked. So how many of you are engineers? How many of you know an engineer? Just checking. So if you look at the earthquake scale, it's logarithmic. So when you have 8.2 versus 9, it's 8 times greater. So, I mean, that is a big difference between an 8.2 and a 9. So 8 times bigger. But what was interesting, that reactor had been over-designed so that all of their safety systems still worked. So they kicked in, they did fine. What got them was the tsunami. And I'll walk through how that happened. So the design worked fine. It was...
If there were so many warnings that area is not good for construction, where was the Nuclear Regulatory Commission of Japan? What were they doing?
They were wimpy. So the regulator in Japan was not an independent nor strong regulator. There was too much collusion. The industry was so powerful, the regulator was not strong and robust, and that was just a standard practice. And not just in nuclear reactors, it's almost in all regulatory. The regulatory structure in Japan was just different. And so that plant was licensed by the government, was approved by the government, was inspected by the government, and it was just not the same. The thing that's interesting is that in 1999, so I'll talk a little bit about the earthquake and the tsunami impact. So when it was designed, it was about a 3.7 meter tsunami was what they predicted. They did an analysis later on, and they predicted that, well, it could go up to 6.5, 6.7 meters. So they went through and they elevated the safety systems to handle almost a 7-meter tsunami. TEPCO's own engineers did a hypothetical calculation in the late 90s. And they said, hypothetically, we could see a tsunami of 16 meters. Everybody said it's not credible. The Japanese government, the Japanese Society of Civil Engineering, TEPCO, the regulator, everybody said not credible. What they should have done is they said, we don't think it's credible. Here's what we would do if it happened. And that's what they did not do. And they got hit with a 14-meter tsunami. That tsunami was devastating. And what's interesting is there are pictures all up and down the East Coast where villages were down by the water, and beautiful villages that are just gone. I mean, there's just all that's left is a few foundations. So when you look at this phenomena, about 18,000 people were killed from the tsunami and the earthquake. And that it just all up and down that coast, villages were just gone. The pictures of before and after are just absolutely stunning. But the force of that water is just amazing. And you look at this area here, it looks like a nuclear bomb went off. I mean, the devastation was stunning. And you look at the water flow, you know, the bridges that used to be there, the roads. This was a picture of a chemical plant that burned for 2 weeks, killed about 34 people from the releases. The other thing that's interesting, people always talk about the radiation. You know, people are just afraid of radiation. I mean, that's the bottom line. It's you can't see it, smell it, taste it, and so your fears kind of kick in. But no one talks about that tsunami pushing all of these chemicals inland, and have now ended. Nobody talks about that, and but they'll be worried about the radiation because it's just perceived as different. You look at the cars were tossed around just like toys. I mean, you just I saw a video of as the tsunami was coming in, the water, and there was a traffic jam, and all of a sudden this individual had a camera on the front of their car, so they recorded all this, and so they're stuck in traffic, and all of a sudden you see these semis going backwards. They were floating and just being carried away, and then ultimately this car that the driver, it started floating and moved around, and the driver fortunately survived. But you know, the amount of destructive force from that water was just amazing. The other thing that's amazing is this is Fukushima. These were the exhaust stacks. And even though the earthquake was 8 times greater than design, these stacks remained intact, which was phenomenal. I mean, the fact that they remained up. At one of the plants, and I'll show you a picture, there was a person that was actually working on one of these towers that was killed because it swayed 3 feet one way, 3 feet the other way, and had injured his head, and they couldn't get up to save him, which was unfortunate. But you look at this wave, as a wave approaches the coast, you know, it'll rise up. So this is a reactor building, this is a turbine generator building, and these pictures are from the security cameras that Fukushima had installed. And so you can see this wave is actually taller than the turbine building, you know, as it comes in. That's a lot of water. I mean, that's just the amount of force there is stunning. This is a reactor that was about 10 kilometers away at Fukushima Daiichi. So the one that had the accident was Fukushima Daiichi, which Daiichi means 1, Daiichi means 2. So this was at the Fukushima Daiichi site, and only 10 kilometers away. But the difference is they maintain a power supply, and I'll show you that in a minute. So they were able, and 4 reactors were running at this site, and they were all brought safely to shutdown. But this, if I've been walking along this area, not when that water was there, but the water was probably about 15 feet deep right here. And what's interesting, the intake for the turbine generators are here. So if you go to a lot of hospitals, where do you think the turbines are? I mean, the emergency generators. They're in the basement. Same thing happened here. All these diesel generators were in the basement for backup power. And so in this one, the water intakes are totally, or the air intakes are totally underwater. So all that water went in, and diesels aren't happy when they have no air and they have no essential cooling. So the diesel generator was running. You can see the smoke up here before the water came in and wiped them out. So the guy that was head of this site was really a hero, because he was able to bring these sites down at Daiichi safely, and they had all 4 running at full power when that tsunami and earthquake hit. So basically what happened in the nuclear business, what you do is you have defense in depth. So you do a lot of backup safety systems. So in general, what happens if you first lose off-site power, then you typically will have multiple power coming in, multiple sites. What was in general, Japan does a great job of their transmission system because they have so many earthquakes, they're robust. But at Fukushima Daiichi, they had a problem where their off-site power, one of their big towers had a landslide. And so they lost off-site power. So in general, that's not a problem because you have backup generators. And so if you need 2 diesel generators to safely cool the reactor, then you'll have another one just in case one of those doesn't start up. So the way those fuel pellets are is like electric stove. If you have an electric stove that's glowing red hot and you turn it off, you don't want to put your hand on that burner or you'll be an unhappy camper. So those fuel pellets, because they're hot, they have a thing called decay heat. So you'll have about 8% of the energy that was being produced. You have to remove it. Otherwise, things get unhappy. And in this case, things got unhappy. So in general, what happens, you have loss of offsite power, your diesels kick in, and that happened. So the diesels kicked in, everything was fine for 45 minutes, and then a tsunami hit. In general, you would be okay if your diesels fail because you have backup batteries that can run for 8 hours that will operate your safety equipment so you'll cool the reactor down without melting the fuel. Their battery compartments were not watertight. In the United States, ours have been watertight since the 80s. And the reason the United States required that was they thought you might have an internal pipe break and you could flood your battery compartment from internal flooding. And so all of our United States battery compartments have been watertight. So if you look at this situation, if your reactor is running at full power and you lose your offsite, you lose your diesels, and you lose your batteries, you are going to melt fuel. I mean, it's just calculate those numbers and that's what's going to happen. So this tsunami that came roaring in, they had thought that it was maximum was going to be about 6.5 meters, 6.7, ended up being 14, and it just rolled right through that whole facility. So let me talk a little bit just quickly about the kind of reactor. So this was a boiling water reactor. In a boiling water reactor, your containment is inside here. So you've probably seen pictures of pressurized water reactors that have that big concrete on the outside. For boiling water reactors, that's different. So this is your containment in here. This is your upper support structure. And this was a picture of a boiling water reactor under construction. And so this is a person standing here. So these are big systems. And so this is where you have your suppression chamber where you condense all your steam back if you have an accident. So there's a lot of safety systems in there. But this is the kind of reactor. So this area up here, this material is really to protect the workers and the facilities from harsh weather, for rain, snow, and so you can work under a variety of conditions. This is not a containment area up here. The containment is this thick concrete structure. So this is all that support structure above the reactor. The reactor is below this concrete area. When your reactor is running at full power, you can actually walk on the top of this because there's very heavy shielding, so you don't have to cross your legs and protect your vital organs or anything like that. It's a safe environment, so there's no really radiation in this area. And so I'll show you in a minute what happened to that containment, both the containment area here and the structure up here. So what happened on the accident is you have your reactor core, all those fuel rods and fuel assemblies. They're hot. Normally their water is flowing by them. If the water stops, they're going to melt. And so for a while they were boiling and water was moving by here. But once they start melting, you have two reactions. One is that cladding around the fuel pellet is made of zirconium. And there's a reaction that if zircaloy is hit with steam it will make zirconium oxide. So from your chemistry, if you snarf off the oxygen from water, what do you have left? And so I'll show you what happened in a minute from that hydrogen. So basically what happened was, in general, this area is vented, but because they lost all their power, including batteries, they couldn't open the valves to vent this facility. So what happened as this melting occurred, your hydrogen and your radioactive elements are coming above that reactor where I said you could normally stand. You wouldn't want to be standing there because this is a very contaminated area now because of the fact that they were not able to vent through filtration that they should have been able to. But their valves, they couldn't open them. They were so big, they had no way of opening them without power. So what happened was it went boom. So this is unit number 1, unit 2, 3, and 4. And then 5 and 6 were over here that were shut down for refueling. So what's interesting, of these 6 reactors, only 3 were running. Only unit 1, 2, and 3. Unit 4 was down for major maintenance. And I'll show you a picture in a minute. So this is what the site looked like. So you had these 4 units here. This is a turbine generator building that wall of water came over. And then what I want you to see is notice all of this area, these big tanks and things of this nature. So what happened, so this is what the site looked like before the accident. Very beautiful site. You know, it's on the side of the mountain. The ocean is there. I mean, it's a beautiful site. This is what it looked like after the accident. All of those tanks that were here, see all of these, all this stuff? Gone. That wall of water just came in and just took them out. And so these were a series of pumps, and so they would stay in there. They had cranes that were back in here that were just knocked over like toys. And I'll show you another picture in a little bit of a vehicle that is actually stuck beside this building. I'll show you what that one looks like. These actually were water tanks that were over here for condensate water. So unit 1 exploded first. And what happened was, when it exploded, it knocked some of the panels off of unit 2. So the hydrogen and the radioactive gases were able to escape. So unit 2 did not have the hydrogen explosion. Unit 3 had a hydrogen explosion. Now, you remember I said unit 4 was shut down? You'll notice that it also had an explosion. So why do you think that happened? If you'll notice, this is a tower that served units 3 and 4. This is a tower that serviced units 1 and 2. And so that's where the gases should have gone up and filtered out all the radioactive elements. You'll notice that this pipe connects here. So the hydrogen came out of here, should have gone up, but the valves were closed. It came over and visited that plant. So early on, there was a feeling that the spent fuel pool in Unit 4 had lost water, and that you had this zirconium steam interaction and you had hydrogen generated. So for a while, the perception was that it was from the spent fuel explosion, and that did not happen. It was really hydrogen came over here and blew. So there were a lot of statements in the press early on that said the spent fuel pool had combusted and basically had a hydrogen explosion. A lot of times when you have an accident like that, the first information is wrong, but it'll get presented over and over again as fact when that's not really a true assessment. So I tell everybody I'm the one that's dressed in white. This is me here. We're on the top of Unit 4 before they removed the spent fuel. And so I've been at that site about 5 times, and you now do not have to dress up like that to visit this particular site because the radiation levels are down. They've cleaned it up. But when you first go in, you have multiple layers, and so you'll actually have 2 white suits, and as you come out of the contaminated area, you'll peel them off, and then eventually you'll get back to your normal clothes. But when you go in there, at that point in time, you had to have breathing as well as multiple layers, so you weren't breathing or getting contaminated. And we were up there looking at the spent fuel pool, and what they were getting ready to do was build a structure to get that spent fuel out of that spent fuel pool. And so, again, this is that tower that's back behind that I am still amazed at that tower. When you think of the forces it saw, 8 times greater than it was designed for, that it still stayed intact. So you notice that car. That's about 30 feet off the ground. And so the flood came in from the left, and this is the turbine generator building. And basically the water was way above this top level, and so it washed this car, and it was wedged, between that structure and the building. So you just think of the forces that building saw. So what they've...
What's the elevation of the control room in that unit? Did that get flooded too?
No, the control room was high enough. It did not get flooded. And it was behind the turbine generator room, so it was in another building. So the control room was further back. So the people that stayed in the control room, they had no lights. They had no emergency lighting. So they're having to use flashlights, and they went out and pulled batteries out of their cars just so they could run lights and try to see their instrumentation, because they had lost all. I mean, it's 20/20 hindsight's great to have, but you think about having a control room and not having emergency lighting, it just doesn't make sense. But that's what they had. So what they've done now is they've built a sealed wall to prevent water that comes down the mountain through that site and into to their bay area. Even in Japan, water flows downhill. And so they're on a massive water flow system. So even before the accident, they were pumping around the reactor site about 1,000 tons of water a day, because the water flow through there is just massive. A lot of very green, a lot of rain. And so because those pumps now are not operating, they wanted to build a retaining wall so they can control and not have seepage of water running through there. So they've built, these were some of their first tanks that they built, because they had to store the water quickly. And so these are basically bolted. You'll see some pictures later. They're now solid, more robust tanks. But they have a lot of water that they need to do a controlled release. But it's very difficult for the Japanese government to go. They have to go through a consensus decision-making process. And so they really do need, this water has been filtered now. The only thing that's left in there is tritium, tritiated water. And so how do you filter water out of water? So hydrogen consists of regular hydrogen, deuterium, and tritium. And so tritium has a 12.3-year half-life, so a lot of that is decayed already. But all of our nuclear plants around the world have a controlled release for tritiated water. It's not a radioactive substance that's a bone seeker like plutonium or other kinds of strontium, for example. They're not. So water, it just passes through. So the biological half-life, if this was tritiated water and you drank some of that, it would not collect in your body and it would pass through. In a biological half-life, lots shorter than the physical half-life. So this is the structure that was on Unit 4 that they were. So this is, you can see the massive destruction when that hydrogen went off. You notice there was no flame. There's just a flash, and nothing burned. I mean, it was just a huge kinetic energy release that caused a lot of structural damage and caused concrete to come out. Just amazing the amount of force that thing, the rubble that they had. So they built so this was the original structure of Unit 4. Because there was a concern about how structurally sound that building was, they didn't want to put any additional weight on that building because they just didn't know. So they built this structure, cantilevered it over, and that's all the cranes that they used to take the spent fuel out of Unit 4 spent fuel pool. So what was really good from my standpoint is I've been trying to get them to get a safety culture awareness and a different way of acting. So after they took the first fuel assembly container out, untypical of Japanese, they stopped, they asked everybody, can we do it better? What worked? What didn't work? How can we do it safer, better? And so they're starting to get a safety culture in where they'll actually communicate, ask questions. They still have an interesting, we did a survey, and 70% of the people still say, if the boss says to do something, even though you know it's wrong, they'll still do it. And we have to get them to change that culture. So on nuclear safety, you always have to have a questioning attitude. And just because somebody says it's safe, you have to think about it. And every day your job is to make sure that plant is safe. And so that it's a work in progress.
Back to the hydrogen explosion in Unit 4, has anybody modeled that? I find it kind of interesting that you can have such a huge energy release that have to be pre-mixed pretty well within the flammability limits, wouldn't it?
I don't know. Probably there's some weird chemists do weird things, so I'm sure somebody has done that. But hydrogen explosions have been well known forever. At 3 Mile Island in the United States, when we had our accident, we had a hydrogen burn inside the containment. So what you'll find now on every reactor is you have hydrogen igniters, so that if you have hydrogen, you'll have sparks that'll detect it and it'll burn it, rather than having an explosion. So, there's a lot of things you can do. So these are the tanks that are around. A lot of tanks. They have about 1,000 tanks with filtered water that everything is out except tritium. And you can see it is a beautiful area. They're much better. People are now being able to come back, so it is getting a better activity. So what we really learned from Fukushima is how do you handle a station blackout? Now, interestingly enough, the United States is much better on station blackout than any other country. Why do you think that was the case, other than having a nice regulator like the NRC? An event. There was an event that caused us to look at that in a different way. What do you think that event was? 9/11. 9/11, September 11th. So the concern was that after we realized people could, instead of making missiles, you could turn an airplane into one. So the issue was, suppose someone would hit a nuclear plant. What would go wrong and how would you protect it? And so the NRC promulgated a lot of rules after 9/11 to enhance the safety of nuclear plants. So we were in a much better position in the U.S. than anyone else. So basically, station blackout is something that everybody around the world is looking at. How do you address station blackout? When you lose all your power like they did, they lost on-site, off-site, diesels, batteries. So how do you do that? The other thing is, because of the perception of was the spent fuel pool drained in Unit 4 or not, so they now they actually have water measurements, so you can tell if there's water in there or not. Like, duh, why wouldn't you have done it before? So things are pretty obvious after things happen. The other thing is, in general, if you have a 2-unit site in the United States, you assume that only one reactor has an accident at a time. Now they're saying, what would you do if you had a problem with both? So multiple units. For new plants, the United States was in pretty good shape. They went back and looked at some earthquake issues, but for the most part, not a lot. China looked at it for about a week and said, yeah, we're good to go. They need the power. I mean, they really have. They're like France, no choice. United Arab Emirates, we took a team over to Japan, talked to people, looked at things, and we did elevate that plant. It's on the Persian Gulf or the Arabian Sea, depending on which way you want to call it, in not a high tsunami area, to say the least, but just to make it safe, they elevated it. Germany determined to shut down their plants before they even knew what happened. That's called politics. Merkel needed the Greens to form her coalition. Italy was about to start their nuclear program. They changed governments about every other day, so that was not a surprise that they would stop. India is going to also have to add more nuclear plants, but they will also look at safety enhancements as well. So with that, see what other questions you might have.
As you think about the places that are building reactors, when you were talking about their siting of the Fukushima plant that had the problems, you described their regulator as weak. If you had to think about the strength of the regulators in these other contexts, what would your sense of them be? And then where do you see the sort of broader safety culture that's being developed in China, in Emirates, and these other locations?
You know, the thing that's a challenge, I think, what works in the U.S. does not necessarily work in other countries. We can't take our values, our culture, and just plop it on someone else. They have to determine what works in their culture. So when I was at the NRC, we had an international nuclear regulators group that would get together. And what was interesting, in the Russian regulator always begged us to help them be a stronger regulator. I mean, when you think about it, being a regulator in Russia, can you imagine going up and telling the operator you're going to shut the plant down? Not. So different governments, different structures are there. So there is no uniform regulatory standards, nor should there be, in a way. There should be some requirements, but countries are going to have to do that on their own. So the way you try to do that, after 3 Mile Island, we created the Institute of Nuclear Power Operations in the U.S. to enhance our training. After Chernobyl, they created the World Organization of Nuclear Operators. But there you get into politics, and it's hard. So for example, the Japan office, they knew that they had a weak regulator. They knew that they had safety issues at these plants, but it's very difficult for them to deal with it. So I think all we can do is I think now that you've had an event like Fukushima, much like after 3 Mile Island, we enhance safety. So the world nuclear plants are going to be much safer because of Fukushima, but the harm of the public perception is hard to overcome, and it'll take time. But I think in general, the young people today are not as afraid of nuclear as people my age. High tech, fast actions. Young people today are much different, their views of nuclear, than others. And so I think at the end of the day, we need safe electricity from a variety of sources. I'm not an expert in climate change. That's not my area. But if you are concerned about climate change, for base load, you're going to have nuclear energy. I mean, the sun doesn't shine all the time and the wind doesn't blow all the time. So for base load, it has to be a part of our energy picture in the whole world.
You may not wish to answer this question, but you had a lot of military experience. You were in the executive environment, you were in the regulatory environment, you know what the military issues are, you know what 9/11 effect was. You put all that together. Can we protect our nuclear reactors from attack?
The answer is yes. Can we protect them against everything? No. The biggest threat that we will always face is the insider threat. And it gets back to people. And so if someone wants to do harm, so you can have all the systems you want in the world, but if you have an employee that's either disgruntled or having mental issues or having a variety of things, you can't stop everything, but you can stop enough. So in my feeling, what keeps me awake, when I was after 9/11, I was at the Pentagon and I had the nuclear, chemical, and biological defense programs. And so what's amazing, we looked at all kinds of terrorist issues that we had a concern about, but we didn't put them on the front page of the paper of saying, go here. What keeps me awake at night is bio threats. I think our nuclear plants are so safe. And what happens from a terrorist standpoint, you want to make your facility so strong and robust that they're going to go somewhere else. So when you pull up to a nuclear plant today and you see all those armed guards and that thick 4.5 foot thick concrete you're going to have to get through for the containment building, they're a hard target. There are a lot of soft targets that are out there. I mean, as an example, we could shut down our gasoline supply with 6 light airplanes with explosives. So, I mean, there's so many other targets that are out there. But what I think is interesting, I talk to the press a lot in Japan, and they always come back to the radiation. No one has died from any radiation from Fukushima. As bad as it is, there has not been a single cancer that has been identified. Now, the government has paid some people because they had like thyroid cancer. They might have had it anyway. But the government has paid for a few cases, but there's been no definitive case, nor is there likely to be any, from the radiation that was released. And so I talked to the Japanese and I said, when you think about it, here you had 18,000 people that died from the earthquake and the tsunami. No one has died from radiation, but there really is this fear of radiation. And the press just instantly came back and said, yeah, but those people are dead and gone. It's the uncertainty that bothers people. And that's something we just, as a society, we have to deal with, no matter what it is. Derek.
I know it's probably worth a whole nother lecture, but do you have a 1-minute answer on what your thoughts are on nuclear waste in the future between Yucca Mountain and reprocessing in the U.S.?
Yeah, I'll make that short. One of my most frustrating activities as chairman of the NRC is that we were not allowed to do our job. Whether Yucca Mountain is safe or not is not up to the President of the United States. It is not up to the Secretary of Energy, and it certainly was not up to Senator Harry Reid from Nevada. It is up to the Nuclear Regulatory Commission. I had 150 people whose job was to read that 8,000-page application. So 8,000 pages was their safety application that referenced over 2 million other documents. So whether Yucca Mountain is safe or not is a decision that the NRC is, by law, it is their job to determine that. So I am a very strong advocate of completing that process. In other words, that by law is a site that was analyzed, that was a site that Congress had picked through a government process. It obviously was not unanimous, but it was almost unanimous to look at that site. Right next to Yucca Mountain is a facility called the Nevada Test Site that about 1,000 devices that release a large amount of energy in a short period of time had been tested, some above ground, some below ground. So they tested nuclear weapons out there. And that site is never going to be a greenfield site. Storing of spent fuel is boring. It just sits there and acts like spent fuel. It's not a dynamic process, and you can have all kinds of measurements. I believe that we can do it safely. Sweden, Finland will have the first sites. We should have done it because we have more knowledge. We studied that site, but politics got us.
You mentioned how the water flow at Fukushima was coming down through the plant area, and I've read that they're trying to have some sort of frozen water curtain, and why that just seems like very energy intensive rather than some, say, a concrete barrier or something.
They are building a frozen wall. I have never been a fan of that frozen wall, but it's because of Dr. Haas's former life. One of his national laboratories in the United States suggested that to the Japanese. And so they're building this frozen wall that goes all the way around that site. And the reason that I'm not in favor of it is for exactly what you said. The cost for what you get is not, in my mind, not worth it. It was a political decision. So they are doing a free wall. So what happens right now, originally, right after the accident, you had 400 tons of water per day that they were collecting. So as I said, even in Japan, water flows downhill. Because the bypass wasn't working, that water would filter into the building. It would get mixed and contaminated with other contaminated water, so they would have to store it. So they would build another tank. I mean, at some point in time, you're going to run out of tank space. So to stop having to build more tanks, they're looking at a variety of things. Now they do have a bypass system where they'll pump the water so it won't go through the site. So that reduced it to about 300 tons. When they get the freeze wall up, they believe that it will knock it down by another maybe 100 to 150 tons. But it's a very expensive process, and I believe they would have been better served to do other things like more pumps, more bypass. That site is hydrologically very complicated because they moved dirt around. You know, they had bulldozers and they leveled it. And my concern has always been they just don't understand the real detailed structure of that water. So you put the freeze, you put that wall, that water is going to go somewhere when it comes down the mountain. Is it going to go around it, that wall? Is it going to go over it? Is it going to come underneath it and cause pressure for water to come up? I just don't think they understand that ground. But that was, they didn't ask me to vote, but I gave my opinion. And it's very expensive. I sarcastically said they needed to start up Unit 5 just to provide electricity to keep that wall frozen. But again, other than the cost, it doesn't hurt, but I think they could have done things more efficient.
So I've got a question, Dale. So I've heard about some interesting projects on thermal storage or storage plus nuclear to allow nuclear plants to load follow more. Can you discuss any of that and what's your view?
France load follows with their plants. When you have 75% of your electricity on one source, you have to load follow. So it can be done. The reason we generally don't do it in the U.S. is cost. So if you have a plant that's running at 100% and you back it off to 50, it's not like you bring in a ton load less of coal every minute. So it doesn't save you that much in operations or people. You still need all the safety systems, you need all the people. So cost per kilowatt, if you back off a nuke plant, rather than running it flat out, then it's just not an efficient operation. But technically we can do it. It's just the fact that it's expensive. And so it's like having your Tesla and driving it at 10 miles an hour. You want to basically drive those things flat out. So the ones that are likely to load follow are these new small modular reactors. So I am on the technical advisory board for NuScale, and they're building inherently safe reactors, 50 megawatts each, little modules. So they will build a 12-unit. In Texas, we'd call that 2 6-packs. So they build, so you have 12 50 megawatts, so you've got 600 megawatts of power. And you can either load follow or you can just shut a unit down because you have so many of them.
And when you shut a unit down, how long before you can bring it back up?
Very quick. So when you shut them down, if you look at, you have a period of most reactors, if you're running them full blast for a while, there's an element called xenon, part of the fission fragments, and it's a storm neutron absorber, so you have to get a xenon override. But for the current design on these, you could either load follow or shut them down. In a day or two, you can bring it back up.
And what about thermal storage combined with nuclear? Isn't there some reason?
You know, I'm still optimistic that John Goodenough is going to win, and he's going to have this battery that is economical. One of our most interesting and simple concepts of storage now is just pumped hydro. So if you look in Europe, at night, France has a surplus of electricity. So what they would do is Sweden would buy that at night, and they have a geography called mountains and a lot of water. So they'll pump water from a low elevation to a high elevation. Then during the day, they would run it downhill, sell that electricity to Germany, and make zillions of dollars. So pumped hydro has been in place for a long time. And right now, it's much less expensive than batteries. Battery storage now it just doesn't work, economically. What was interesting is Idaho National Lab is looking at a concept. Out in Idaho, they have mountains, but they don't have a lot of water. And they don't have a lot of, right now, cheap electricity, except what they're doing is wind and solar when it's surplus. They're loading these rail cars with heavy rocks and pulling up the mountain. And then when they need the peak, here comes the train down. And actually, when you think about it, the only thing they're losing are the frictional losses of pulling that train up and the frictional losses coming down. And they haven't really looked at the total economics. But I think we'll look at alternatives like that. But I think before it happens on a utility scale, We really need John Goodenough, Dr. Goodenough, to come up with our new battery. Yeah.
He's been doing a lot.
Yeah.
We want you to use the microphone so it's recorded also, since these are videotaped.
One
Any
last
more
question.
questions?
I have a comment and a concern. The questions of safety and regulation, they are partly cultural and partly because of the way that modern institutions are set up. Take an example from India. It has a very sophisticated system of education, but still no university or any other laboratory does nuclear engineering. So therefore, everyone who is in the nuclear engineering field is trained by the Department of Atomic Energy in one of its labs, whether it be in Bombay or wherever. So when there is a Nuclear Regulatory Commission of India, everyone there is again manned by precisely the people who were trained in a certain order, even if they don't obey their bosses blindly, right? But their entire orientation is exactly conditioned by the people who make the reactors and run the reactors, all right? So it becomes awfully difficult then to expect that they would be able to discharge their duties properly. So it's absolutely important. So that's what scares me. New countries, no infrastructure of education, no independent nuclear engineers apart from the Department of Atomic Energy, etc. And that is something which, on a larger issue, level, one has to do. Even when a big country like India doesn't quite have that. I'll be very worried about UAE, and
Well, the fact that I go to the UAE a lot, their formula, I think that UAE did it about as good as anybody can do it. They first passed laws. They established a regulatory body, an independent regulatory body. They hired the former executive director of operations from the NRC, who had been at the NRC for like 30 years, to set up their regulations. And the thing that they have that I think is they have a questioning attitude. So the Emiratis will, if they think something, if they don't understand it or they think it's questioned, they have a good questioning attitude. That coupled with the technology being as developed as it is, that reactor, the Korean, and initially the combustion engineering design is well understood. So I think you can do it safely, you can do it right. Can you do 100% risk-free? No way. But one of the difficulties I think we have, there is no source of electricity that is risk-free. And so we have to make choices. And so if you ask someone if you would like, a nuclear plant next door, it was no. Do you want a coal-fired plant? It's hell no. And so you go through all of these, and when you look at it, it's interesting to me, if you look at wind eats birds and bats by the millions when you look at all of our wind. Bats, when they fly close to those turbines, there's a low pressure, and the membrane of the bat is very fragile, and so they explode. And you look underneath any windmill, you're going to see dead things. And so, that has its challenges. You look at chemicals used to make solar panels. How do you handle that? So nothing is risk-free. And so you just have to make the best choices you can. And I think our best strategy is diversity.
right, no, I agree, but I think you made a statement that somehow nuclear energy strikes some primitive fear in people, and they're willing to take hundreds and thousands of people dying from fumes and chemical products, but even the possibility of a single death by radiation somehow seems to scare the people. So in some sense, we have to, in the nuclear system, we have to be just so much more careful than somehow the society allows for chemical systems or any other thing.
You absolutely do, because the consequences. What you do in a nuclear plant is no different than flying. You have a low probability, high consequence event. And that is why that's why nuclear safety has to be so high. That's why it has to be strong and rigorous. Well, I think due to time, let me stop now and I'll take more questions.
Sure. Thank you again, Dr. Klein. So thank you very much for an informative talk, as always. So next week, please join us Our speaker will be Dr. David Biello, science curator for TED. He will be speaking on energy and the Anthropocene, and that term relates to human activity that has been dominant in the influence on climate and environment. So thank you again.